Okay, so we're going to talk about this week's problems. This week, there are a couple of easier problems, and then I want to do a little bit of geometry. They're not too hard, but just to get people used to the idea of thinking about geometry. Um, Again, I'm going to assume that you have read the problem, and so I'm just going to get right to it. The first problem, you have 100 obstacles, up to 100 obstacles, the numbers between 0 to n minus 1. And then you're going to be given a list of obstacles that Mario has found, and you have to figure out basically how many he has found. But some of these numbers can be duplicated, and also you have to list all the ones that are not found. So the fact that it's only up to 100 basically means that you can just use Boolean array indexed by the ID to say whether you have seen it or not. And I guess you just do that, and then at the end, just go through the list from 0 to n minus 1 and see which ones have been found. So I don't really want to spend too much time on this one, but I'll just quickly show you my code. Um, so I read in n and y. I have a Boolean array that says whether I've seen that obstacle or not, and I initialize everything to false. Now, in case you didn't know, when you initialize an array of size whatever, you're supposed to put in the number of values that are that's the size of the array. So in this case, I have 100 values, but I only put in one. When you're missing any values, then automatically it's filled in with zeros. Okay, so it's not filled in with false, but it's filled in 0, which in this case happens to be false. However, if I try to initialize this whole array by true, I cannot just write true once because it'll just be true and then a bunch of false. So there's a little bit tricky way of doing things. If you know what's going on, then this works. Otherwise, you can write a loop to initialize it. Or you can use a vector. Um, so alternatively, you can use vector who seen, and then you can say and then false like this, and this will initialize all of them to be false. Or if you want to initialize them to true, you can do true. Okay, anyway, that's just how I initialize it. The problem itself is not that hard. And then basically I just read in all the values, all the obstacles, IDs that you find, and then I set it to true. Okay, if I see something multiple times, it will still set it to true just once. Okay, and then after that, I remember how many I found. And for each one, I go through all of them. And, if it's not found, then I got to print it, right? Otherwise, I just remember that I found one more thing. Because at the end of the day, I have to produce how many obstacles he's found. Okay, so that just keeps a count. There's probably not much more to say. It's fairly straightforward. So move on to the next one. Okay, the next one is a little bit of, I guess, a little bit messy string manipulation thing. Basically, you have two words, P and Y, Y and P, and then you're supposed to form a new word that is Y and P with something added in between, but Y, depending on how Y ends, you might have to modify certain things. So the standard rule is Y followed by the string EX followed by the string P. But then the exception, so if Y ends with just the word, just E itself, then you only add the X. If Y is a vowel other than an E, we remove that final vowel and then add EX. So basically any vowels at the end, it's replaced by E followed by an X. If y already ends with ex, then you don't have the ex. Um, so basically, you just have to check for all these exceptions and then work on it. Now, another thing that's important is that all these strings are the only lowercase English letters and at least two characters long. This is perhaps the more important part, at least two characters long. Why? Because at some point I might want to ask, does y ends with ex? If the string always have at least two characters and I don't have to worry about, checking for the last two characters and running it out of bounds because I always will have at least two characters. Okay. If I can have strings that have only one character and try to look at the last two characters, I might go to bounds. When I look at the second last character, there might not be a second last character. And I'll end up looking at, I don't know, the index -1 or something like that. So just to make sure this is at least two is important. At least 10 is not that important. But anyway, so again, I don't really have much more to say other than just show you the code. So just want to show you how I do it. So I read in Y and P. Now, this is something I like to do. If I am looking for, is it one of the following characters? In this case, is it A, E, I, or U? What I would do instead of writing an if statement that have 5 different conditions, right? If it's A or if it's E and so on, what I'm going to do, what I'm going to do instead is I'm going to have a string containing all the characters that I want to check for. And then I'm going to use string search. I'm going to say, look at the last character of Y, so Y dot back. In any containers, dot back is the last character, the last item in the container. So Y dot back is the last character. So I do a string search of the character Y dot back, and I ask, is the character inside the string? In other words, is it one of these vowels? And this is a way for me to easily figure out if it's a vowel. So it's a linear search, but it would be the same thing if you write 5 if statements, right? If or you use an or, if it is an A or it's an E or it's I and so on. So I use string.find, and then string.find is supposed to return the position where it's found, or if it's not found, it returns a special constant called string : and post. Okay, so this says that whatever it returns, it's not the special location, therefore it's found. So that's I guess the only check that I want to say. All right, so the answer, it's what I'm trying to build. If the last character of Y is an E, then all I do is an X. Otherwise, if the last character is a vowel, then I remove that vowel. So with strings, you can do pop back. So didn't know. C++ basic string has a pop back function. Okay. And in general, you can look up, what are the functions that you can do with basic strings. And there's a back, for example, that's what I use. And then pop back. Now, what is this dr star? Okay, let's see what this dr star means. Actually, I don't know what this dr star means. No idea. Let me see if I can find it somewhere. What is this dr star? dr11. Actually, no, okay, hang on. Dr, the number NN after dr denotes target C++ revision. The defect report is applied to. Hover over star to see additional notes. Okay, so I'm not really sure what dr star stands for, but maybe it's something that wasn't working before. Now it's added or something like that. Back since C++ 20. Uh-huh. So it's C++98. The following behavior changing with defect reply. Okay. Oh, okay. So it's retroactively applied to previously published standards. So even though um, it's introduced later, it's retroactively applied to previous one. Okay. That's what that means. Okay. So anyway, um, didn't have dot back before, but now it does. That's what that means. Okay. And then I check if the last two characters are EX, right? So the last character will be an X. And then the second last one is Y dot length -2. So again, if length is not at least 2, this could go out bounds, right? So if length is 1, this would be Y bracket -1. So that's not good. And then finally, if all else fails, then it's a normal case, so you just add EX. And then we bring it up. Okay. Now, the first two, I said that this was supposed to be something about geometry, but first two problems just warm up, has nothing to do with geometry. Okay, so the next problem is where the geometry comes from. And basically, you're given a bunch of shapes, either rectangles or circles. If it's rectangle, it's given, the description is the two corners, x1, y1, and x2, y2, and they guarantee that x1 is less than y1. So x1 is less than x2, y1 is less than y2. If it's a circle, you have the center at xy, and then a radius between 0 and 1,000. And the important thing is that everything's integers. Okay. And then after that, you have a bunch of x and y, and you're supposed to figure out for each point how many shapes are contain this point. And contain, if it touches, it says the boundary of a target is inside the target. So if it touches the boundary, it's also considered to be inside. Everything are integers between -100, 1,000 to 1,000. So the question is, if I have a rectangle, and I have a point x comma y, how do I know if that point is inside or not? Well, if it's inside, then x has to be between x1 and between x2. It's less than or equal to, because on the boundary, it's considered to be inside. And same thing with y. So if you want to know if a point is inside a rectangle, then you just do this check. Now, of course, when you write this, you cannot write it this way because this is a binary comparison. It will return true or false, which will also be converted to 1 and 0, and then they will be compared to x2, which is not nonsense. So what you have to do is you have to write each of these separately. I guess if we're using, hang on, using C++ notation, I should be writing this either. So you're writing like this. Okay, so that's how you check if if a point is inside a rectangle. What about circle? Okay, so you have the center of the circle and radius. So we have radius, and then let's call it Cx and Cy, the center of the circle. And now you have a certain point. You want to know if this point is inside the circle or not. How do we know all the points inside the circle satisfy that the distance between the point and the center is less than or equal to r? That's what it means to be in a circle. Okay, it has to be equals because you could be on the boundary. Okay, so how do we compute the distance? It's x minus cx squared plus y minus cy squared, Pythagoras, square root is less than or equal to r. And that's your test. But you never want to do this because remember that all of the quantities x, y, cx, cy, and r, they are all integers. And when you do this, this is an integer. Inside here is an integer, but as soon as you take the square root, it might not be an integer anymore. And so even if you have, I don't know, inside is 25, when you take a square root, it's going to be some approximation of 5. And it may not be exactly 5. It might be off by a little bit. And if you have exactly 5 here, right on the boundaries, with the rounding error, you might accidentally think that it's outside or inside. Oh, well, maybe you think that accidentally is outside even though it's right on the boundary. So we don't want to introduce floating point numbers if we don't have to. Okay. So what we want to do is to avoid floating point numbers by squaring both sides. So instead, we will compute the distance squared has to be less than or equal to r squared. Now, we have to worry a little bit, perhaps, because when we square numbers, then things are going to get bigger. So are we going to have to worry about overflow? Well, we know that x and cx are between negative 1,000 to 1,000, and r is at most 1,000. So if r is at most 1,000, then r squared is at most 1 million, which is well within the range of a normal 32-bit integer. And here, if x and cx can be at most 1,000 or negative 1,000 or worse, this can become, it's at most the absolute value. So how do I write this? The absolute value of this thing is at most 2,000 because the worst it can get is one of them is negative 1,000 and the other one is positive 1,000. So the distance is 2,000. And then when you square it, it's at most 4 million. So again, well within the range of a 32-bit integers, which is up to 2 billion. Okay, so now we don't have to worry about using longer integer. We can just use int. So basically that's it. Okay. Um, and then I want to show you my code. I'm not quite sure why I wrote the code that way, but maybe I was a little bit bored and I want to write it in an object-oriented way. You don't have to do this, but that's what I did. Oh yeah, runtime error. Why did I have runtime error? Because I actually didn't read the inputs. But anyway, I didn't bother checking. I called, what did I do? Yeah, I forgot to call read or something like that. Anyway, so I decided to have a class called shape, which has two things that it can do. It can read and it can decide if a point hits that square, that shape. Okay, so this is I don't know, a little bit fancy way, I guess, of doing it. It's a abstract class, abstract base class, because it has these pure virtual functions that are not implemented. If you didn't know what the heck this means, forget it. You can write it in whatever way you want. Um, and then uh, I have two different types of shapes. One is called rectangle, and then they're both subclasses. So rectangle has four things: x1, y1, x2, y2, and then it overrides the two functions. Oh, actually, you see this is bad because hit should just be a const function for those of you that care about this stuff, because hit is not supposed to change the data of the parameters of defining a shape. So this should be a const. And let me just add it and resubmit. This should be a const. And then these are const. Okay, so to see if a particular point x and y is inside the hits the rectangle, then I do this check, which is what I wrote before. And then to read, I just do that. Read it from cin, and then I do something similar for circle. So here I do dx, which is the distance between x minus cx, dy is y minus cy, and then basically this is the dx squared plus dy squared is less than equal to r squared. Now, I know that some people would be tempted to square something. Some people might be tempted to write pow dx comma 2. Do not do this, because pow is a floating point function and it will return a floating point value. So someday I can tell you more about the story that once upon a time I wrote this code. Let's say answer equals to this, and to try to take 3 square, and when I print cout answer, well, what do we get? Those of you that have heard me tell you the story, you know what the answer might be. When I print that out that one day, it was 8. Why? Because 3 square, even though it's supposed to be 9, this returns a floating point value, and this function happens to return 8.999 whatever that day on that particular machine, which when I convert it into an int and store it, it drops these things and becomes 8. And so I couldn't figure out why my code was losing one once in a while. And that was the reason. Okay, anyhow. So this is done through what we call polymorphism in C++. So I have a vector of shape stars, and basically for each shape, I figure out what type I'm supposed to read. If it's a rectangle, I create a new rectangle object and set S to point to that. Otherwise, I use circle. I create a circle and set S to point to that. S.SL read will call the correct read function, and then I push it back to the vector. So now I have a vector of shapes. And then for each point that I read in CXY, I remember how many hit, and then I just go through all the shapes and ask, does it hit it? And if so, update the count. And that's how I do that particular problem. Okay. So this is kind of a little bit of a warm up, I guess, but still, the most important that I want to point out is the fact that you almost never want to compute the square roots if you can avoid it. Okay, so if they give you floating point numbers as input, but like I said, you can't really do much about this. And if you don't actually need the distance itself, but you're using distance as compared to some other distance, most likely the best way to do it is to use squares, distances, so you don't have to worry about rounded errors. Okay, next one. Now this time you cannot avoid floating point numbers because you're supposed to produce floating point numbers in your answer. And they will tell you that you're supposed to produce answers that are basically correct up to 3 decimal digits. The last decimal digit could be a little bit off. Okay. So what is the problem? You have a circular cookie and this of a certain radius, and this center is always 0, 0. You're gonna cut the cookie at a certain point xy, and it's supposed to go through the line of cut is supposed to go to the chord. Okay, so now the shorter chord. So what the heck is a chord? Okay, so you draw from the center to this point. Okay, that's of course the radius. And then you go perpendicular to this, and that's a chord. Now there's actually a second chord that you can draw, but the problem says you want the shorter of the two. So what is the second chord that you can do? You can, actually there are other chords, there are many other chords. You can, for example, just go here and go this way, right? Or you can go here and then go some other way. Okay, but these are not the shortest chord. The shortest chord arrives from drawing a line from the center of the circle to your point and then going perpendicular. Okay, so that's the first thing that you have to remember. And then you have to basically figure out the area of these two parts. Okay, so just put different colors and then print it out. There's a third possibility. The third possibility is the point that you pick, it's not even inside the circle. And then you say miss. Okay, so this is what you have to do. How do we know if it's a miss? Well, we just did that before. We compute the distance squared. Right? Because the center's the origin 0, 0, the distance squared is just x squared plus y squared. So if this, I guess, sorry, if it's this, then it's missed. Now you might say, well, I just told you, so you're given these, input that are floating point numbers. What if somebody just try to hit it really, really close? Or maybe like right next to it, right next to the boundary, either inside or outside. So are we going to be accidentally get this comparison wrong because of rounding error? And the answer is normally, maybe, but they tell you that no strike will be within 0.001 centimeter of the edge of the cookie. So as long as you use something that has more digits of accuracy than 3, you will not be fooled because you will not be that close to the boundary. That's what they say. So as long as you use something like double, you're fine. Now, you might say, well, how many digits of accuracy you have? So you can look up this IEEE 754 format, and you should almost never use float unless somebody tells you you must use float. You probably should just use doubles. So double is binary 64, so double precision. It tells you that there are 53 digits, but these are binary. So decimal digits are about almost 16 digits of precision. Okay, so that's plenty. Now, there's something called quadruple precision. If you really, really want, you can use quadruple precision, and these are called long doubles in C++. And that gives you even more precisions. But for most problems, you don't need that. Okay, so that's if you are inside or outside. So now let's suppose that you're inside and you hit somewhere. How do I figure out the areas of the two parts? Okay, so the first thing is the whole circle. It's of course pi times r squared. How do you get pi? Well, there's no easy way to get pi. So if you look at the unit circle, for example, pi is 180 degrees. So cosine of -1, it's pi, which means that pi, it's the arc cos of -1. So in C++, you can just ask for a cos of -1, and that will give you pi. Okay, that's the easiest way to get pi. In newer version of C++, this is a predefined constant, but not in C++ 17, which is what's supported in Caddis. Okay, so you can get the error circle. Now the question is, how do I get this? Or the other way, okay, whichever way. Because if I get one piece, I get the other one. Now you always have to worry, I guess, what if this point is some sort of boundary condition, so we have to worry about. Well, if this point is on the boundary, then this cut might not make a lot of sense, but they already told you that no cut will be on the boundary. So we don't have to worry about that. So that's good. What if the cut is right in the center and split it in two? Well, that's definitely allowed. So we have to make sure that whatever we end up doing will take care of this case. All right, so how are we going to do this? The easiest thing to do is to draw a triangle like this, a wedge. We know that these are the radius of the circle, so they all are. We know what this distance is because we know x and y. So this distance, if you want to call it, is x squared plus y squared square root. And now we have a right angle triangle. So this part is r squared minus d squared square root. Okay, let's call it b. So this is Pythagoras running backwards. B squared plus d squared equals r squared. So to solve for b, you get this. So this area here, it's just b times d over 2. But you got two of these. So the whole triangle, the wedge triangle, this triangle, just this part, is b times d. Okay? So this part, it's b times d and belongs to the large chunk. So now the next question is, what about this other part? Okay. So this other part has a certain angle, theta. So if theta out of 360, if we talk about degrees, that would be the portion of the circle times pi r squared. Okay. So this, you have to figure out what the angle is, divide by 360, or if actually it's better to work on radians. So we don't work with 360, we work at 2 pi. And actually that makes things easier because this pi cancels out. So if you know what theta is, then just theta over 2 times r squared. And that would be this green area. And the green area plus the blue area will be the large chunk. And then the small chunk, of course, is just the rest of it. So subtract that from the area of a circle. Okay, so how do we get this theta? Okay, so we'll draw this again. Okay, if you note this is D and this is R, then this angle, okay, so let's use a different symbol because I have theta again. So let's use psi. We know from trigonometry the cosine of psi is equals to D over R. So psi is the inverse cosine of D over R. And then theta is just 2 pi minus 2 of psi because it's one side over here and the other side on the other side. And that's pretty much it. Once you know this theta, you can plug it into here to get the green area by theta times r squared. So theta over 2 times r squared. And then once you have the green area, add the blue area, that's a large chunk. And then the small chunk is the large chunk subtracted from the area of the total circle. Now, we always have to worry about special cases, right? So I draw this like there's a triangle, but when does this fall apart? It falls apart when, let me erase this, when the cut point, it's right at the center of the circle. And you cut right here. Okay, because now you can't really draw a chord. But does this still work? Does our formula still work? Okay. So the triangle part that we have here, well, if x and y, you cut right at the center, then x and y is 0, 0. So d is 0. So the triangle part is 0, which is fine because there is no triangle part. What about this part? Does it work? Well, if you have d is 0, then you're taking arc cos of 0. And if you use this unit circle, 0, this is x equal to 0, so cosine of 0 is 1. Wait, sorry. What am I trying to tell you? No, that's not what I'm trying to. Cosine of 0 is 1, but that's not what I'm trying to say. Cosine of uh, pi over 2, because that's 90 degrees, cosine of pi over 2 is 1. So it's 0. So arc cos of 0 is pi over 2. So pi over 2 times pi over 2 times 2 is just pi. So this becomes pi. 2 pi minus pi is pi. So altogether, when we plug in this formula, it's pi r squared over 2, which is basically saying it's half the circle, which is exactly what we have. So this formula just works out even when you have this case, but it's always good to check when you have geometry problem, you work out some formula based on some diagram. You always have to ask yourself, is this diagram the whole truth? Or are there some special case where your diagram may not make sense and you want to make sure that your diagram or all your formulas work even in those cases or everything fall apart? Okay, so that's that one. So at the end, the code is actually relatively short, right? But um, it's not about the length of the code, but how you get there. Okay, so um, not, and then at the end you compute the two pieces, and then just in case I have to print the larger of the two pieces, so I swap it. And then the only other thing that I want to point out in this code is how to print it to more than a certain number of digits, so fixed, and then set precision the number of digits. That's how you print. Okay. Okay, the last one is a little bit more involved. Um, I guess in terms of thinking anyway. So you have a convex shape. So what does convex mean? Convex means that if you pick any 2 points inside the shape, you draw a straight line, that line will not go out the shape. So for example, here's a shape that is not convex, because if you pick 2 points here and draw a straight line, that line can go outside of the shape. So this is what is called concave. And this is called convex. Convex will never have. When you draw any line between 2 points in this shape, that line stays completely inside. Okay, so now you want to figure out what is the shortest width, the min width of this channel that allows you to slide the coin, this shape down. And you're allowed to rotate this shape. So how do we approach this? The first thing to realize is here, there's a bit of a gap right here. If the sides is not touching the shape, then you could have make it smaller, make the width smaller. So there is no reason to have any gaps between the wall and the shape. Well, of course you can cross over. And if I draw this properly, then the shape must touch on both sides of this walls. But is that the best thing, right? So, for example, let's just make a shape triangle. If you rotate it, let's say this way, until one of the sides sits flat, then this is going to be better. When you rotate it, this will rotate with you and you'll end up being shorter. And basically, with this argument, you can say that there's no reason not to have at least one of the sides against the wall. Okay. So one of the sides must be against the wall. Which sides? Well, we don't know. So what we're going to have to do is try all the sides. There are only 20 sides at most, so we can try all of them. Now, how are we going to try all of them? Let's say we try this one. Where is the other side going to be? Well, what we're going to do is we're going to have to figure out how far we have to go this way to reach all the other points. So you're going to have to figure out the distance of each of these other points to this line. And the distance is a perpendicular distance. Okay. So now we are basically asking a different problem. You have a line which is defined by some points A and B, and it's an infinite line. So even if you have a point C here, the distance is the perpendicular going to this infinite line. So how do we figure this out? And this is where having some linear algebra could be useful. So if you draw the line from A to C, right, you can figure that out. You can figure out the distance and the so on. You can figure out the distance from A to B, right? So, and then from there, because this is a right angle triangle, so let's call this D. This distance and this distance, these three distances satisfy the Pythagoras theorem. Okay. Now the problem is, this distance between A and C is known, but you don't know these two right now. So we have to figure out where this point D is, I guess. So if you know the angle, then all you have to do is you have to say the distance from A to D, this distance, let's call it capital D, and then let's call this capital C. Then cosine of theta, it's equals to D over C, C over D. And so D is C divided by cos theta, if you know what theta is. So how do we know theta? And this is where the linear algebra have to come in. If these are vectors, so this is U and this is V, then there's something called a dot product which says U dot V, it's equals to cosine of theta times the length of U times the length of V. So V is from A to B, which you know, and U is so all of these you know. And so you can actually figure this. In fact, you don't even need to figure out theta, you can just figure out cosine of theta, which is U dot V, dot product. If you don't know what that is, we'll talk about that. These are the length. So if you have a vector, if U is UX, YX, UY, V is Vx, Vy, and the length of U is the square root of Ux squared plus Uy squared. So you do have to compute the square root, okay? And V, the length of V is likewise, and then U dot V is just the x components multiplied together plus the y components multiplied together. So we can figure out what this is, and then we know that this distance d is c divided by the cosine of this. So cosine of this was this. Because we're dividing by a fraction, we can put this thing up. And actually c is actually the length of u. So you can write it like this. And once you have this d, and you know c, then you can do c squared minus d squared square root would be this distance. Okay, so you can work through all that math and implement this, or you can say, go to my code library, and among many, many functions, or actually maybe we go to the one level above, there's an index that tells you what are some of the things that you can do. And we're looking for geometry. And one of them is called distance line. Compute the distance of a point to a line, which is exactly what we need. So you go and look this up. It's already implemented for you. And compute the distance from C to the line defined by A and B. So you give your A and B for the line and point C, and then this code does it. Okay, it does it in a somewhat different way because there are multiple ways of doing the same thing, but it's equivalent to what I wrote. So with that in mind, let me show you the code. You might think this is cheating, but in the programming contest, it's about, finding the right tools that you already have implemented, and you can use that. So I have 20 points, up to 20 points, which is the polygon. I can read in the x and y coordinates. And then I try all the different lines. So each line is between the ith point and the next point, but with a polygon, but inside I have to worry about the sides from 0 to 1, 1 to 2, 2 to 3, and so on, but also from n-1 back to 0. So that's what I do here. And then for each of the boundary that I checked, I compute the distance of that point to the line, and then I keep a running maximum because that's the furthest point I have based on that line, and that's as far as I have to go. But then once I manage to figure out what is the maximum I have over all these points, I want to keep a running minimum out of all the boundaries that I try. So I have some really big number initializing, and then every step I compute the current minimum of all the different boundaries that I try. So I don't actually physically rotate the boundary of the polygon, but rather I compute the distance of the boundaries to all the points, and I try all the boundaries. That's how I do this problem. So if you want to think about this, what is the complexity? It's n double loop, it's n squared. So yeah, n is 20, so it doesn't really matter. But even if n is 1,000, this is only a million iterations, so it's definitely good enough. Okay, so for this week, I'll stop here. And if you haven't done them already, please go and try them.